Thank you very much for coming to the Friday Seminar today. I'm going to try to do things a little bit different. I've received some good positive feedback from grey-haired people in the room, so I'm going to try and run these slightly differently. Just as a starting point, the different videos of the Friday Seminars are posted online for those of you who don't know. So if you miss a week, you should be able to come back and see these. They're on YouTube. So if you just search Sustainable Minerals Institute or SMIUQ on YouTube, you should be able to find some of the past presentations that are available online. But I'll get back into welcoming Ben. So Ben's going to be presenting today on the measurement of rock competence. Ben's been at JKMRC for a number of years now, but he did his undergraduate at the University of Toulouse in France, and then went in chemical engineering, and then went straight through a PhD with Florent Bourgeois. I can't say his name properly, but he did a PhD under him. Some of you in the room will know Florent from his time at JK, and in sequestration of CO2 through carbonization of minerals. And then straight after that came to the JKMRC, where he's followed up from some of Florent's work on the short impact load cell, for those of you who know the work that he did in the 90s, and kind of continued that work through, and in the vein of Marcelo Tavares and those kind of researchers has continued the measurement of rock strength and looking at meaningful measurements of rock strength. So for those of you who don't like the title today, blame Malcolm and myself. We kind of decided that this should be his title and encouraged him to present on this. So yeah, enjoy the presentation. I'll just pass it over to Ben.
Thanks, Jean, and thanks for having me. It's actually going to be exactly 4 years I joined JK next week, so it's kind of a milestone for me. And so today what I'm going to present is the research we've been doing with Malcolm and the group, the communication group, in trying to change our view on breakage testing and kind of implement new tools, bring a new paradigm in breakage testing by using impact load cell and strength measurements. So trying to shift from empirically derived parameters to really mechanical parameters. So just as a disclaimer, all the work that I'm going to present today is not 100% my work, but it's more to give you a framework about what can be done as well with those kinds of devices. So the outline of the presentation is current approach, of course, what we do now, what we do well, and obviously the current limitations that comes with it. Then I'm going to spend a little bit of time talking about the impact load cells and the device, so just a little bit about how the device works, because I've heard different things around the JK saying that we can measure this or that, we can measure UCS strength and those kinds of parameters. Not exactly, so I'm going to get back to the basics. I'm going to spend a little bit of time explaining how that works, so to bring everyone up to speed on those devices. And because we have the technology here available at the JK and we want to make use of it. And then I'm going to spend a little bit of time saying 4 case studies where basically we've applied this technology, or some other groups, like in Brazil, the Brazilian teams have applied, and what we can do with it, and then future applications, what we are looking at for the future applications with using those devices. So when I talk about breakage testing today, I'm going to talk about single particle breakage. So this is quite important. We're not going to talk about bed breakage or batch testing. This is really particulate testing, and we're going to study breakage of single particles. Well, this is essential for communication modeling, and it's at the heart of the JK for many years. And the JK has had leadership in the area, twin pendulum, torque weight test, RBT. And of course, recognized as a national international standard. The well-known empirical relationships that we've seen, I've just put the T10 versus ECS, or with the new MPQ, is the energy to product fineness relationship. So this is a well-known relationship and it works, and it's useful for empirical modeling. But the current testing in dot weight and RBT has limitations. The first one is the size range. For dot weight test 13 mm, for the RBT 5 mm. What happens for particle less than that? So the effect of particle size has been tackled. There is the relationship between AB and MPQ, but then basically the AB, or the measure of hardness, kind of loses its purpose with the MPQ, where it becomes harder to compare an MPQ with another MPQ. What happens for AB over 100? We know that for very soft material, the model has limitations. What about the variability? So when you test 30 particles in the dot weight, there's a standard per side, it's 30 particles. You might have 30 different answers. 30 particles might be actually different. How do you capture this variability? And the last one is the low energy impact. Okay, what happens if actually I use less than the minimum energy available in a dot weight or in an RBT? What about damage accumulation, repeated impacts? Those devices have limitations. So this brings the motivation. Why using those impact load cells and what they can be used for? So first is getting away from empirical parameters to mechanical properties that control the breakage. So we can measure that with those. This can bring the effect of particle size on fracture properties. So the fact that we know that the particle gets harder or stronger or, when they get finer. So those devices can capture this kind of properties. And we do individual particle testing. So each particle is a different data point in the test. Okay? This brings an underlying breakage probability, and we'll talk about that a bit later. But first, a little bit of history about the impact load cells. So it's a hybridization of a drop weight tester and a Hopkinson bar. A Hopkinson pressure bar was invented by this man, Bertram Hopkinson, a British mechanical engineer, that was doing the study of ballistic and detonation impact. And basically the concept about this device was that you can study the strain wave propagation in a steel rod where the length of the wave is longer than the diameter of the bar. Okay? And basically in 1980s, or even before, his paper is 1940s, not 1914, sorry. Hopkinson had actually a pendulum. It was hanging from the roof. It was a steel bar with ropes, and he was studying, well, basically was shooting bullets to the end of the impact and was looking at the movement of the bar. Okay, so this was very random, but the principle is the same. You study the propagation of a stress wave in a steel bar. The impact load cell used for mineral characterization was then invented as the impact load cell in the University of Utah in 1986 by the team of King and Herbst, and they were basically using this bar here, which is the Hopkinson bar, putting a particle on top of it and dropping a ball mass, steel ball on the particle. So this is the drop weight part of the device, and this is the Hopkinson bar. So they basically said, we're going to use the Hopkinson bar principle to study the particle fraction. So this graph is actually taken from Bourgeois' thesis in 1994, and they had some pretty old electronics and amplification. Nowadays, there are much more advanced ways of capturing that. The whole strain wave is captured by strain gauge. So strain gauge are attached to the rod, and we capture the stress wave as it goes through the rod. Okay. So this is quite an advanced version of the Hopkinson bar compared to what this man did in 1914. It has been used. It has been studied since about 20 years now. So the team in Utah basically worked until 1998, where Marcelo Tavares, the Brazilian team, now in Brazil. They studied 27 brittle ores and material with this, and they compared the 27, so coal ore, copper ore, glass materials, any type of brittle material. They characterized it with this device, and they have all the data. So they did an incredible work to show the application of this, and they were able to compare, well, a coal strength with basically a copper ore all the time. Now a history of impact load cell at the JKMRC. So this is not the first time that this device was studied here. In 2002, Bourgeois, after his PhD in Utah, joined the JK here as a postdoc. And then he actually designed a portable version of the device. And the aim of that was to create a device to make in situ measurements. So he wanted to bring that device on site to make measurement. So they designed a portable version, like a shorter version that can be moved around. In 2009, Rodney Hawking, supervised by Randolph and Peter Hoekman. Sorry, this is the first device that was designed in 2002. So this is roughly my height. It's this big, so it's fairly small. This is the same device, but revised by Rodney Hawking, that studied the impact and the acoustic measurements around the impact. They had microphones around the particle, looking at acoustic measurements and X-ray tomography when the particle was breaking. Rajiv had to look at the device as well to look at the effect of shape in 2010, and CIST 2013. This is the device how I found it. We had to completely recommission the device, just as a fun fact. There is actually no bar in the device when I found it. So when I arrived in 2013, Malcolm said, go and recommission the impact load cell. I found it in the shed. There was no bar inside. It was completely rusted. I had to basically rebuild it from scratch. So since 2013, we had one MPhil, two PhDs, Fatima and Paris, that worked on the device, and we have two prospective students in 2016 that will potentially use it. So this is the history of impact load cell at the JKMRC. So this is just a little animation to show you the principle. So this is again the Hopkinson bar there, the flat end, and the ball, the release mechanism, and the strain gauge links to an amplifier and that deviation. So that works, that doesn't work. So you release the ball falls on the particle. There's a trigger event. When the ball touches the particle, the signal starts recording. The impact speed is usually 1 to 2 meters per second. It's usually in Doppler tester. And well, the difference between the impact speed and the propagation of the stress wave in the steel rod is large. So you see this compressive strain wave in the rod is roughly 5,000 meters per second. So this is much higher than the impact speed. So that helps to actually expand the force applied on the particle. The stress wave goes down in the rod, is sensed by the strain gauge, and then you record the signal. You record the voltage, and the voltage is actually related to the force applied on the particle. So then you have the force versus time profile. Okay? And this is what typically is used in compression testing. You look at the force and the deformation of the device, of a particle in the device. The short version of that is only 1.5 meters. The trick about this device and what was designed here in 2002 is the deconvolution analysis. So this shows that when the compression wave is going to hit the bottom of the bar, it's going to be reflected, and it's going to be transformed into a tensile wave. So actually the bar is going to vibrate like that. Very quickly, so this time is in seconds. So it can actually travel up and down in less than microseconds. But by knowing the length of the bar and the properties of the rod, you can predict when this signal here is going to come back. And by doing that, you can do deconvolution of the signal. The application is shown here. We've broken a particle. The blue signal is the signal sensed by the strain gauge. So you can see that there is a fracture, and then the reflective signal comes back and then travels in the rod up and down. The deconvoluted signal, after calculation of the prediction of when the wave is going to come back, is shown here in orange, and this comes back to 0, so it's like the rod would be infinite and we don't have the reflection coming back. Okay? So why is it useful? As I said, here the voltage is measured by the strain gauge, and actually the voltage is related to the force. That's just by applying a known force on the bar and recording the voltage, using the voltage and the force, and it's a linear relationship. So then you've come up with the force and the time profile. So this is a particle being broken, the particle is being compressed, the force is applied on the particle, and at this point the particle can't sustain the force and breaks. There is failure. When the particle breaks, it actually loses contact between the bar and the ball, and the force applied on the bar is going to drop. So this point is called the first fracture, and it's a mechanical properties. It's how much force or strain or stress, the particle can sustain before fracture. Here is the internal reflection, so that's just when the particle starts to be compressed, the compression wave can actually be reflected within the sample, so that's just an artifact of the device, but that doesn't cause any issues. And this is secondary breakage. So after the first breakage, when the particle fractures, the ball is still moving on the fragments and is being fractured again. The fragments are being captured. And this was covered by Fatima in her work that studied the effect of the momentum of the ball falling on the particle and having re-breakage and using this information. But at the moment we just use this information, which is the actual particle. So, okay, we've done one test, we've broken one particle. We have actually more than one information. There's a total of 4 parameters that can be derived from one breakage even of one particle. And this is by doing a momentum balance around the particle. So here you see the particle at initial contact and during impact. So the ball is moving down, the rod is moving down, and the particle is being compressed. The deformation of the particle, or the strain applied on the particle, is actually the difference between the movement of the ball and the movement of the bar. By doing an integral, which is the area below the force time curve, you get the fracture energy. And this is a very important parameter. This is how much energy has been absorbed by the particle until it fractures. When it fractures, it's the fracture energy. Another parameter, or another property that can be derived is the strength. This is assuming a spherical particle. And using the fracture force, the strength this is in megapascal, so it's the same as the force, can be estimated. And the stiffness of the particle, the stiffness is like the elastic properties. The elastic properties are related to the stiffness of the tools, which is the stiffness of the steel, of the bar, and the stiffness of the ball. By doing a ratio of the stiffness observed and the maximum compression at fracture, then you can estimate the stiffness of the particle. So this is quite a lot of information just by doing one impact. So then, what you do when you do a silk test, you actually will take a sample of your ore. You have, let's say, 30 particles. There's maybe a little bit more here. And then you break them independently. You measure the fracture force, the fracture energy. So then you have 30 different values. What you do then is you rank them from the minimum to the maximum, and you plot them on the log axis. And this is what happens. This is a log normal distribution of the fracture energy. So this is the fracture energy we calculated before. So what we can see here is that there is a distribution of strength. There is a distribution of properties within the material. So this is again one sample. I didn't split it, I didn't do anything to it. It's just one sample taken out of copper. There are 2 properties here that can be observed. First is the average fracture force, which is these points here, and we're going to call it the E50, which is the 50% to break, the energy to break 50% of the particles. The line that you can see here on the graph is actually a model that was derived a long time ago and has two parameters. First one is the E50 and the second one is the geometric variance of the distribution, which is basically saying how much this curve is spread, okay? If this number is higher, the curve is going to spread, so highly variable ore. There's a lot of different strength in the ore. If this number is small, then the curve is going to be sharp and there's not a lot of variation in the ore, okay? Or variability. So this this probability distribution can be observed for all the parameters: the stiffness, the strength, the fracture force, and the fracture energy. All the four parameters can be plotted this way. This actually is quite interesting because it gives a lot more information than just a breakage test where you apply energy and you size the product. And by the way, we're not sizing the product here. We're not looking at the product size distribution. Once the particle is fractured, we just discard it. It's been split in two. We're not looking at the product size distribution. We're not really interested in that because we are just interested in the compression and fracture force and fracture energy. And then you do that. So this sample was one size fraction. We do different size fraction. You can see here the same sample, but plotted for 3 different size fractions. And you can observe that they have different average, E50, and different variation, different variability or geometrical variance of the distribution. And what was shown here about the team in Utah and Marcelo is the relationship between the E50, so this is this value versus size. So when you take this value, energy, and those size, you plot it on a log-log scale, and what you observe is this. So this is a quite important relationship. And there is a model actually that follows this trend. And what Marcelo observed is that when the particles are large, the fracture is controlled by crack propagation. So actually, when the particles are large, and it could be a pebble on 50 millimeters, there is a lot of cracks, there is a lot of damage, faults in the particle. And the fracture is controlled by what's the length between those cracks? What's the distribution of those cracks in the particles? When the particles get really fine, the fracture is controlled by crack initiation. So basically you have a grain and you have a particle that has less faults or cracks. And the fracture energy is going to go up because you're going to need to activate cracks within this structure or texture. Okay? And then you have only 3 parameters, which is phi, D0, and E infinite, which is this value here, which is basically saying that the specific energy here doesn't increase much. If you have really large blocks or down to pebble size, roughly the energy to break them is similar, the specific energy. Okay, so with all this, so we've seen that this device is available. We can measure different material properties, and so how can we use them? And this is 4 case studies that we've been conducted here at the JKMRC, backed with some data from the Brazilian dogs. The first one is comparing ore strength of cut and blasted rocks. So this is a study I'm going to present. So just a 4 case HPGR private quickening. We're going to look at what's the effect of the HPGR on the particle strength, the effect of shape when we test nearly spherical or cylinders, and the effect of alteration on the breakage properties, and this is a work by Bragg. Okay, the first one was a study conducted in the Anglo Center here at the JKMRC. And the question was, what is the effect of rock cutting? So this is a rock cutter at a mine face versus blasting. So you drill and blast, or you just have a cutting machine that continuously cut the rock at the face. Well, Anglo was interested in what are the properties of the material after you've been through blasting or through cutting. The impact load cells and the information you get out of it was the perfect device to assess that. The ore was UG2, a platinum ore. You can see the size distributions here. This is the blasted rock, so it has a coarser size because of the blast being not selective. The cut rock has a much smaller top size. Because of the cutting mechanism, you can produce actually smaller, can control the top size produced. But interestingly, the blast rock size in the fine end, down to -1 millimeter, was actually finer. So this says that actually the blasting produced a little bit more fines compared to the rock cutting machine. So we did AB, we did rotary breakage tester, and this is the AB values we found. So because this is UG2, this is a nasty ore, so really high AB. And this is because of the chromite particles. So the chromite agglomerates are quite soft and they break preferentially, they break quite easily. So I said, well, actually, the numbers are all over the place and I can't really compare them. So I went on and carried the impact load cell test to look at the properties and trying to get away from those numbers that were included. But before doing that, we had another look at the UG2 and we found out that the breakage properties was driven by the composition of the ore. So this is roughly how the ore was divided. We had a look at the tomography. So the first phase was chromite particles, and the second one was more silicate phase. And you can see there, the chromite grains are the bright little grains in this picture, and those particles are actually quite soft. They break easily, and you can find them in different ratios in the ore. So this is one not easy because when actually you test AB, well, you test those two particles. It's the bulk sample. You take it, you break, and you have the outcomes of the different components. This is the impact load cell results, specific fracture energy of the silicate in blue and the chromite in green. So you can see that there is a significant difference on the log scale between the E50s of this ore and this one. So this says that actually if I test the bulk, I have like a bimodal distribution of strength. I have one very soft, one very hard. So I went on and did the test on the cut rock and the blast rock. This is the curve here plotted for only a very narrow size fraction. So what I'm looking at here is only a tiny little bit of this curve, but this is enough for this test. And what was found is that there is no significant difference between the cut and the blast product. They have roughly the same strength properties. But what we also found is that when you plot the chromite and the silicate together, you find that they have the different strength, they have different size, different strength with the size relationship. And that the actual strength of the ore is driven by the composition. What we later found out, and I'm not going to go in details here, is that the blast and the cut rock had different proportion of the components. So the one that had the more chromite was actually softer. But it's not because of the cutting mechanism, the blasting mechanism, but just because of the composition. Okay. The case study 2 here, we're going to look at the HPGR product weakening. So it's well known that you put an ore through an HPGR, it's going to be softer. This is the work published by Bianca. Bianca looked at the AD properties of the HPGR product with different pressures. Here the graph shows the increment in AB with the HPGR operating pressure. And she found a significant increase in AB, so a softening of the ore. But she also found out that the bond work index was not increasing significantly compared to the A. Okay. So basically it was in the order of a few %, 1 or 2. So then I was wondering, okay, can strength measurement back that up? Okay, can we confirm that by doing strength measurement? And I've used here Marcelo Tavares data, which shows, again, the mass specific, the median specific fracture energy, so in the E50, which is the properties we're going to look at, versus size. This line here is the HPGR product, and those two lines here are crushed products, so not going through an HPGR. And what was found is that there is a critical size at about 1 to 2 millimeter. Well, the particle properties are roughly the same if they've been through a HPGR or through a crusher. But for larger particle size, that's where the HPGR product has a much smaller fracture energy, so a softer product, and that the difference observed here was actually roughly in the same range as was Bianca's observed. Plus, she said that the bond work index increment was less than the AB increment. So basically, when you test those particles here in this range, which is the -3 millimeter test in the bond test, the 3 millimeter bond work index, well, roughly they all have the same strength. And this is why she said, well, the AB increment was only a few percent compared to the AB increment, where in the large particle size, well, the difference was higher. So again, here the impact strength measurement have been used to back up the what was observed so in the literature here by Bianca and the well-known weakening effect of the HPGR product. In terms of damage accumulation, we also conducted a little study here when we looked at breakage by a damage accumulation. So what happens if you have a particle and you impact it, you don't impact it enough to break it, but just to create like damage accumulation. So we've impacted cubes. This is a little video of the cubes being broken here on the silk, on the impact load cell. And this is the fracture force obtained for an intact cube, so a cube that was not damaged. And here, it's a damaged cube that was impacted 20 times. So with the same cube, we've impacted it until, without breaking it. And this is the fracture force. So there is a clear relationship between the damage that was accumulated in the rock and the fracture force. So again, another application for the impact load cell to assess the damage accumulation. By the way, there's a model to predict what is the reduction here in strength and in fracture force, depending on the number of impacts you've applied. And so. The effect of shape. So this is the third case study we've conducted here. And the reason is that when you test two different samples, what sometimes happens is that you have the fracture force distribution, and the two distributions are actually very close to each other. So there are statistical methods to trying to assess if they are different. You look at the spread, you look at the average, you look at different properties, and sometimes it's just impossible to differentiate two distributions. So then we said, well, actually, some of the variability that we can observe here is due to the shape. So on the left side here is just a roughly spherical particle, but it's got rough corners and it's got rough geometry, and that can increase the variability that we observe here. So we said, well, if we have a control shape like this cylinder, can we actually steepen that distribution, make it steeper, so the actual two distribution will be different and we can statistically differentiate them. Okay. So this is the motivation behind looking at the shape and wanted to test regular shape. But Rajiv in his thesis said from the compressive test it was shown that apparent compressive strength and elasticity are dependent on the shape of the particles and the loading conditions. The limitation of the current strength test standards, which are inadequate when the shapes of brittle materials are studied. And the silk, well, didn't miss that. Spot on. The shape was at the heart of the hypothesis used for all the calculations. So basically, when you switch from this shape to this shape, all the calculations I've shown before, they fall apart. Okay? They're not valid anymore. And so I went on and I looked at the actual geometry of the contact. So this is on the left side, a roughly spherical particle. This is the ball falling on the particle and the particle on the bar. And well, the contact area between the bar, the particle and the ball are circles. So this is based on the Hertzian contact theory. Okay? The Hertzian contact theory says that the compression and the dimension of this circle of contact is related to the force and the geometry of the particle and the ball and the bar. Okay, so this can be predicted. It's easy when it's spherical because it's a circle of contact. Okay, so imagine like the squash ball that you hit a wall. The squash ball compresses, and there is a relationship between the stiffness of the ball, the stiffness of the wall, and this is all correlated based on very well-known theory. What happens when you have here a cylinder shape on the bar? Between the cylinder and the plane, you have a rectangular contact. So this is a line contact, not a circle anymore. Between the ball and the cylinder, you have actually an elliptical contact. And this is because of the shape of the cylinder. So as I said, all the calculation theory was based on the Hudson contact, which is this. With the cylindrical shape, the deformation of each of the area here and there are actually described by other theories and that have been derived that are much more complex. But so far, the impact load cell were only used with the equations on the left, never with those on the right. So I had to rederive all the equations. And what I did is I simply used the calculation of energy and force, which is the integral of the force versus deformation, like the area under the stress strain curve, and used those parameters to recalculate the actual bricade parameter, the fracture energy, the stiffness, etc. So I went on and I did a test with basalt sample. I drilled with a drill in a basalt sample, and here on the black symbols are the crushed particles. So this is the roughly spherical, irregular shaped particles. And the empty symbols, the circles here, show the results with the cylindrical particles. So indeed, the variance of the distribution was divided by 10. So we managed to get the same fracture energy, but with a much steeper distribution. So this was quite interesting, and the application I'm going to show you in a minute of this. So this actually test was, I've done all the calculation for Barris. So Barris did his PhD here on the study of process alteration index and relating that to strength parameters. So I'm not going to go into a lot of details about how he assessed alteration. It's a physic alteration, porphyro, and it's got values of replacement of plagiar clouds, quartz addition. So it was basically looking at what are the alteration properties and how can they be measured in impact load cells, and what's the link with the whole processability of the sample. Okay. Yep. So there's a paper on this that explains how they actually estimated the replacement of plagiar clouds and quartz by XRD. So I invite you to read that paper. So the results are shown here. So on the left side, Barris did the test with the irregular shaped particles and looked at the E50 as a function of the addition of quartz or the replacement of plagiar clouds, like his process alteration index. So on the left side, you can see that the correlation between the E50, so the breakage properties, the kind of look that there is a relationship, so it's getting softer, or the E50 is reducing when the alteration is increasing, and the same case here, but you can see that the correlation factor are quite low, and that with using the irregular shaped particles, well, he wasn't able to actually differentiate the distribution. So that's what I shown before, where the distributions are actually very close to each other. On the right hand side, you can see the same ore or the same alteration profile, but by using the mini core. So the mini core are the cylinders. So now by using the cylinders, he's shown that there is a strong correlation between this process alteration index, or the alteration measures, which is the elevations of quartz or replacement of plagiar clouds. And you can see the increase in the correlation factor was significant. So there is a significant softening of the ore with the actual alteration properties. And it can be quantified. How much was that reduced? Okay. in terms of specific fracture energy. So this was the conclusion there, successful reduction of the variability. So this is really an application of what I showed before, and then it demonstrated the relationship with the process alteration. And then I'm just going to go quickly through two different work that is going on here at the JK. The first one is mechanistic modeling. So what I haven't told you yet is how can we use those measures into a comminution model? How are we going to use that? Are we going to be better off not doing drop weight but doing impact load cell? And then looking at another application with texture and strength. Tools for mechanistic modeling. What I believe is that, and I think what we're going to draw in the next future is that a comminution model should account for breakage probability. So basically, when you have a collision event, the particle not necessarily break, and by DEM, we are informed that there is a lot of collision energy that are only actual low energy impacts. So the actual breakage probability should be a key feature of mechanistic modeling. So basically, what happens when there is an impact, by a particle is being impacted, does it break? So you use the breakage probability. By breakage probability, what people have shown is that this distribution of strength is actually exactly the same as the probability. So I've measured the particles independently here. Each one has a different value. But if I take the same sample, and if I now apply exactly this energy here, by impacting all the particles, what happens is that you will have exactly 20% broken. Okay? So you can already, with this curve, predict what the breakage probability will be. That's just because statistically in the sample you have 20% of the particles that have a fracture energy below this energy, and 80% that have a fracture energy more than this energy. So you're going to need to apply more than their fracture energy to break them. Okay? So then, if the particle didn't break, does the particle have surface breakage? Yes, no. You have different progeny and appearance function in the case of surface breakage. And if it didn't break and it didn't have surface damage or abrasion, does it have damage accumulation? So this is quite important as well, because during those low energy collisions, you will have damage accumulation. As I said before, there is a model to model the damage accumulation, and what will happen is that the breakage probability is going to transform into a new one after the impact event. So this new breakage probability is then going to be fed back for the next step of simulation when the particle is being impacted again. Its properties actually will change. Okay. And so I believe that this framework should be in the heart of the mechanistic modeling, and this is something we're going to pursue with Dion, Weatherly, and Malcolm Powell with the development of the UCM, the Unified Comminution Model. And this is really a vehicle for the outcomes of those tests. So if we can model the breakage with this, if we can manage to do that, then all the parameters we've extracted from the breakage tests can be used in a useful model. At the moment, there's still a decorrelation and this is not fully implemented. But I strongly believe this is a way forward to use this information. And the last one is texture and strength measurement. So I just wanted to show you this work that was actually done by Florent Bourgeois, my previous supervisor. He was still looking at using this device to investigate weakening and texture properties, making texture and strength. That was the work done in France. So that's concrete. So what they've done is they were studying concrete and concrete breakage for recycling. So this is a kind of a picture of texture of concrete, the big grey, this is 2D slice, the big grey aggregates, and the different fractures within the concrete. So what they were looking at is there any texture, macroscopic texture properties that are related to the fracture properties we can measure on the impact load cell? And the first graph on the left shows a reduction in the fracture force. So this is the force you need to apply on the concrete to break it. So this is a reduction in fracture force related to the total inclusion porosity. So the porosity is actually a texture, macroscopic texture properties. So here they've correlated the porosity with the fracture force. So this is already showing that there are textural properties that drives the mechanical breakage. The other graph here on the right is the same related fracture force, so the reduction in the force necessary to break the particle. And you see a reduction in the fracture force with the length of the secondary fracture network. So the secondary fracture network is that they went on and they measured the length of those little cracks here. They measured how much crack they are per surface area. So this is in meter of crack per square meter. So this is, if that is, let's say, 1 square meter, how much length of those cracks in the particles, and they related that to the fracture properties, the reduction in the fracture. So basically what this says is that the more secondary fracture, like those little ones you have in the matrix, the softer the product. And this can be assessed with impact loads. And so this is really a space to watch, and there is a student starting here, PI is going to get these kinds of properties in a PhD work, so just keep an eye on that in the next future. So these are the conclusions. So we had a look at the impact loads there, what they can be used for. We can measure those mechanical properties. We can estimate fracture probability. We can estimate ore viability by doing this test. And it was proven useful in the different case studies. So the study of the cut and blast, studying the composition and the effect of cutting and blasting, the effect of damage accumulation by HPGR, weakening or by repeated impact. We studied the particle shape and the effect on sizing. And then we've seen the useful application of that varies with the alteration index and the strength relationship and the work in progress I just got. But before we wrap up, I just wanted to open this on just trying to think, are we here by using the device as a step change in comminution testing and breakage testing? And I've used what Tim Nepperman recently showed in the presentation for Del Pratt lecture. That was last month. And I basically said, well, I'm going to benchmark this technology against the different drivers for innovation or the barriers to innovation and look at what can we improve, where can we take it, what can we do better. Loss and skills of experience. Let's extract it from your presentation, Tim. Well, we've been pretty bad at this. There are here 7 years and again 5 years in between the different cycles that this device was used here. So, so this is quite interesting to see that actually people come, develop a technology, they work on it, and they're trying to get to improve the methodology and develop relationships, etc. But then you lose the skills, and you have someone else like me coming in, and you need to restart from scratch, you need to recommission the device, rebuild the knowledge. So this is something we haven't been doing well. So how do we keep that going? There was a comment on FIFO, but I'm not going to talk about this because it's not applicable. Decline in industry and innovation needs. Interestingly, there was a pathway to commercialization. In 2002, the SIRP device was a portable device for in-situ measurement. So I think they developed that device in order to have a commercialization pathway. They wanted to build the device, sell it, send it to site. People can measure the different strength and distribution of their ore coming as a daily basis. So there was a way forward. So there was a link with the industry, and I think we still have an opportunity here with JKMRC, maybe a potential user of the device or developer, I don't know. So there are ways of looking at that. The average innovation time constant is 15 years. Well, what I've done is I've plotted electron scopus, and this is the number of publications per year. This is 1993, since the first one by Bourgeois, and this is us today, 2016. So we're happy. So this meets the requirement. This has been around for 20 plus years, and it's well beyond the 15 years time frame for innovation. This is quite interesting. I mean, we are at a stage where we know a lot about the technology and we are able to develop it further. And the other interesting thing that links to the loss of skills and experience in the cycles, you can see the publication cycles went up and down between the different people moving around. Marcelo finishing his thesis, moving to Brazil and starting up the work again. And we are here, I believe we are on a rising curve, and we're going to have more publications, and we're going to take it to another cycle, and hopefully we won't work with it. Obsession with IP. This is a good one. We don't have any issues. There's no patent. The technology is fully published. It's well known. It's there available. And the silo mentality. Well, this is the one that we've been pretty bad at. We have well-known, validated empirical measures for low hardness. We have the AV, we have the knowledge, we have the architect that is the word leader. But we have this technology coming up. And how do we then build a relationship between those two? How do we get the industry to consider those mechanical tests, the mechanical properties, the impact load cell test as another industry standard? And I think for that we really need a model framework to take up the properties. And to look at outside the box, basically, to look at this. So this is the end. Acknowledgement is the Anglo Center and the Vice Chancellor for funding me to carry out this work and to help the students. The students, Barish, of course, Bianca, to help me with to give me some information and to help me to improve my work. Really, Barish came to me with this issue, and we kind of solved the problems for his application. Dion for the good discussions we had about mechanical fracture and bringing the geomechanical vision into the picture, helping me with the experiments, and Fatima for her PhD work, the vacation students, Tracy, Edward, Vincent, and Mika, so this is the UQ student. They did a lot of tests for me on the impact of the cell. This is time consuming, and they did like 5,000 particle impact to help with the cut and blast characterization. The JKMRC students, Fahad, Yogesh, and the UFRJ team, because of the discussions we had and the ongoing work engagement we have with them. Thank you, this is it.